I can already write y plus 2 to the 10th power in the denominator. And now let's see what we have in the numerator. The top function prime will be 4, y minus 1 to the 3rd, times the denominator, because it happens that y minus 1 prime is 1. Excellent. Very good. Then minus. I copy the first function, and now I differentiate the denominator, which will give us 5, y plus 2 to the 4th, lucky me, times the inner function prime, which is 1. Good. Now, I said that before, and I hope I'm not going to see it on the test. Anyone will simplify this with this. How come I can't do it? I want to simplify 5 of these with 5 of these. Because these are terms. These are terms. Yes. I have to factor out the greatest common factor first. Excellent. So can anyone give us the greatest common factor?
Y minus 1 cubed.
Y minus 1 to the 3rd. Awesome. And?
Y plus 2 to the 4th.
Excellent. Well done. Great job. Okay, now let's see what is left from the first term. 4 is left. What else?
Y plus 2.
And a y plus 2. And now I reach the minus symbol.
What about the 5?
I need to put the 5 in. Awesome. Great job. Now you see, yes, please.
So you want to change the y from dy dx?
This one?
No, in the function. The y minus 1.
Yes.
When you differentiate it, you want to do like
Would it be times dy over dx?
Y is not a function. Y is not a function. Y is a variable here. Because you have f of y instead of having f of x. You have f of y. This is not implicit differentiation. Very good point. So in this case, y is just a variable. Takes the place of x. Good point. Thank you, Nate. Okay, minus 5. Parentheses y minus 1. Do we all agree with that? We have to, now we are allowed to remove 4 of those and remove 4 from the denominator. So this will be y minus 1 to the 3rd, and this is 4y plus 8 minus 5y plus 5. Everything divided by y plus 2 to the 6th. We combine like terms in parentheses. Y minus 1 to the 3rd, negative y plus 13, divided by y plus 2 to the 6th. This problem should be in your notes. Minus in front, y minus 1 to the 3rd, y minus 13 over y plus 2 to the 6th. Any questions on this? Anyone? Any questions here, please? It will make me very proud and very happy if you would get really, really, really ready for this test. Okay, let me also say something. I don't like wasting your time with stories. I'm just going to say one sentence. I don't like grading at all. I don't. Here's what I like to do when I grade a paper. So, okay, watch me grade a paper. This is what I want. This is how I want to grade your papers. That's how I would like. Please help me. I want each paper to take me 30 seconds at the most. But if I have to think, okay, this is 25 points. Maybe I can give 10. Maybe I can give 12. Maybe he started on the right track. Then it takes me 15 minutes, one test. So please help me finish grading in less than 10 minutes.
Give us more questions. Give us one big question.
Okay, moving on. So please, that's my dream. That's my dream. That's as much as I want to spend on grading. So please help me. I'll give extra credit if you do that to me. Okay, so x sine y plus cosine x equals y cubed. This time it's very clear. We are asked to find dy over dx. What does this mean? What does this imply? Implies that y is a
Function of x.
excellent. Great. Good. So since we're asked to determine this, then we will differentiate the left-hand side, and we will differentiate the right-hand side. The left-hand side,
Sine y.
sine y plus x times cosine y times dy over dx. Plus, yes, negative sine x equals
3y times dy.
Do you all agree with this? Awesome. Yes, Braden, go ahead.
I'm just confused in the beginning. Wouldn't it be sine y plus that should be a shouldn't that be a cosine x, not cosine y?
So here, this is the first function, and this is the second function. The first function prime times the second plus the first function times the second function prime. But since y is inside cosine x and it's also a function of x, I have to multiply by dy over dx. Is that okay?
Yes.
Minus, you can write plus, I just wanted to show where it's coming from. I wrote plus first, and then minus sine x, because when I differentiate cosine, I get negative sine x. And on the other side, I'm using the chain rule with the power rule. So 3 function squared times the function prime. Is this okay? Good. So now we know we are after these two terms. So the left-hand side will be sine y minus sine x. If you look in your notes, I'm sure this is a problem we've covered in class, or very similar. When I move this term to the other side, I will factor out dy over dx. So I have 3y squared minus x cosine y, and I pulled out dy over dx. Yes. So now in order to find dy over dx, all you have to do is divide by the right parentheses. So sine y minus sine x, 3y squared minus x cosine y. Any questions? Yes, please.
So you subtracted x and cosine y?
Yes, I had to move it to the other side. When I move a term from the left to the right, it becomes negative. Or if it's positive, it changes its sign. But then since both of them had this piece that I'm interested in, I had to factor it out, which is here now.
So the right-hand side would be 3y squared minus 2y dx
Minus x.
2y dx.
This is one term. This is a product, one term. It's not minus x minus cosine minus dx over dx. It's just one term together. Is that okay? Very good question. If you don't ask questions, I will not be able to anticipate or answer the question if I don't know what you see versus what I see. So all your questions help me and help you. Yes, please. Sorry.
How did you get rid of the d1 dx the second one?
I didn't. I factored it out. It's right here. 3y squared dy over dx is this piece.
Mm-hmm.
Negative x cosine y dy over dx is this piece.
Okay, so you just moved it to one side.
I have to because I'm after this variable.
Right.
So I have to have the terms with the variable on one side and factor out the variable.
Okay.
The variable is just this, because that's what I'm solving for. Very good question. Anything else here? Anything else? Okay, next problem. We have y equals tangent x raised to x squared. Any suggestions?
Logarithmic.
Yes. Yes, because it's a function raised to another function. We have no rule for this. There is no rule. The only possibility is to apply log to both sides and then implicitly differentiate to get dy over dx. That's why this is called, the process is called logarithmic differentiation. Okay, so then we have dy equals x squared times natural log of tangent x. I meant to write natural log. I'm sorry. You can't get away with anything. Sorry. I meant natural log, of course. I said natural log and I wrote dy instead. My apologies. Okay, so then y prime, natural log y prime and the other side. Okay, so this is 1 over y dy over dx. Do we understand the left-hand side? Everyone, please?
Yes.
Okay, the right-hand side, remember it's a product. And now you see again, you cannot say natural log times tangent. Natural log is applied to tangent. So this function is the x for natural log. So they cannot be separated. Okay. Now, 2x times natural log of tangent x. Agreed with that? Plus x squared. Now, I differentiate the log, which is 1 over tangent x times secant squared x. Again, I think we even had this on the quiz, not just on homework or class. Okay, so I know you didn't like when I did 2 steps in one, so I'm going to wait for this, or multiply by y first. So let's simplify tiny bit here. 1 over y dy over dx equals 2x natural log of tangent x plus x squared secant squared over tangent x. So now dy over dx is y times all this. But I cannot leave it in terms of y. I have to go back after that, write it one more time, and replace this by this. So this is 2x natural log tangent x plus x squared secant squared over tangent x. And then I copy the same thing one more time, replacing y by what we were given initially, which is tangent x raised to x squared to x natural log tangent x plus x squared secant squared over tangent x. The next problem was done in class and also on the quiz. You want to do it again? Is that a yes?
Yeah.
Perfect. Okay, so we are given the cost function. And when I copy it now, I'm going to copy it correctly in descending order. 0.0005 x cubed minus 0.1 x squared plus 12x plus 1200. We are asked to find the marginal cost function. How do I find the marginal cost function?
Find C prime.
Exactly. Any questions? Anyone? Okay. C prime is the marginal cost. Is the derivative of the cost the rate of change? It gives the rate of change of cost, but it's also called marginal cost. So this is 0.0015 x squared, yes, minus 0.2x plus 12. Excellent. Part B. Find C prime of 200. If you have the answer, don't be shy. Give it to me.
$32.
$32. It's a rate of change per unit. So please remember, Every time you determine the rate of change or C prime or P prime or any F prime, that result has a measurement unit that is a ratio. So something coming from the numerator over something coming from the denominator. Okay, compare your answer from part B with the cost of producing the 200. So what is the meaning is, it predicts the cost of 201st item. And we know why. So remember delta y approximately dy, where this is f of x plus dx minus f of x, and this is f prime of x dx. Like we did many times before, f of x plus a little bit is approximately f of x plus f prime of x dx. This is the 100 and this is the 1. So C prime of 200, because C prime of 200 will be this quantity. This is C prime of 200. C prime of 200 times 1. And this is, of course, f of, this was 200. I'm sorry, not 100, 200. And this is f of 200. That's the reason why. So C prime of 200 predicts the cost of the 201st item. Okay, part C. Compare your answer from part B with the cost of producing the 201st with the exact cost. How do I determine the exact cost? The exact cost is delta C, which is C of 101 minus C of 100. This is the exact cost of producing the, oh, I'm sorry. For some reason, in my brain, 200 is the same with 100. Today, just today. So, my apologies. I will put, I know it's not the same. Okay, Ron is already calculating in dollars. The 200 is not the same with 100. Okay, thank you very much. I know it's not. It's a big difference, I know. Okay, so let's put in the cost function in the graphing calculator. 0.0005 x cubed. If you have the answer, don't torture me. Give me the answer. So minus 0.1 x squared plus 12x plus 1200. So I will have to show what is 201 and 200. I really wanted to put 100 one more time to see if you say anything, but I said I'm not going to torture them. It's okay. It's enough. Okay, so always go and highlight it because it may be that some decimals are hidden in there, and they are. So 3632.2005 and minus, the other one is clean 3600. Because you want to show that those two numbers are similar. And those numbers are similar, $32.2005 per unit. And they are very close. Any questions for me? Yes, please.
So that's the final answer.
That's the final answer for part C. So
You don't have to
compare your answer with the cost. So I'm going to say as a comparison, so the C prime of, I know. So this is $32 per unit. So, which says that they are very close. Very close.
Do you not subtract?
No, you don't have
C
to.
prime of-
No, you just have to say they're very close. That's good enough.
But no, like for the final answer, we got 32.2005.
Yeah, you just have to say that these two numbers are very close to each other.
You don't subtract the C.
No.
Okay.
No, we're not looking for an overestimated number or underestimated. No. Okay, any questions here? Please, Jared, go ahead. 1 second. Yes.
So did you plug 201 into the C prime function?
Yes, I was given this.
Okay.
I can check if there is any doubt. I doubt there is anything wrong here, but I think it's correct, but I can check. So a 0.0015 multiplied by 200 squared and minus 0.2 times 200 and plus 12. I don't think Braden made an error here. He didn't. So it's 32. Very good. Furthermore, the difference of the exact cost is so close. So I was certain that he was right. Okay, use differentials to estimate sine 89. I'm less interested in the number. I'm more interested in the technique, right? So remember, you don't have to memorize this, but once you understand this relationship, you will know where this is coming from, right? So this is f of x plus dx, which is approximately f of x plus f prime of x dx. And we have sine of 89 degrees. So we have to identify the function. We have to identify x. We have to identify dx. And of course, f prime of x. Once I have all these, the problem is solved. Mm-hmm. Absolutely. F of x is sine x. X,
90.
of course. Something that we are familiar with, and it's a nice number, an integer, of course, and close to the angle that we have, which is 89 degrees. Good. Dx. Yes, it is -1, but remember, you can plug in, if it's inside a function, you can plug in degrees or radians. But you are going to have to use this alone. It must be in radians, not in degrees. So it's -pi over 180. How much is f prime?
Cosine x.
Cosine x. Good. So now let's put everything together and we are done with this problem. So this piece is this. This is what we're interested in. And this will be approximately. So sine 89 degrees is approximately. Now I have f of x and I have x. So I have to write sine 90. Then I have to write plus, but since dx is negative, I'm going to write negative. I have to write f prime of 90, which is cosine, right? Cosine of 90. And multiplied by pi over 180. This is what you have to present. I'm sorry? -5 over 180, I put minus in front. Now you can write that this is equal. From this point on, we can write the equal symbol. Sine 90 is 1. Cosine 90 is
0.
That's it. So now we can check, if you'd like. So look at the mode. I have to check its radians. Okay. So I want sine 89. Of course, it's not going to be 1, right? But we are happy with the approximation, right? So it was in radians. So let me change it. Sorry, because I put degrees. So careful, careful, careful. It is 0.999. It's not going to be 1. It's very close. Yes, please, Brandon.
So when we got 1, do you not use the pi over 180?
But this is 0. So minus 0 times pi over 180 is 1. Cosine 90 degrees is 0, and then you multiply by pi over 180. Good. The extra credit. So we have xy equals 8. Any questions? And we have the point 4 comma 2. Any questions? Any questions? Please ask. Yes, Mark. Any questions? Go ahead. Any questions?
So on the last one.
Yes,
answer
this
is-
one
Yeah.
or this one?
No, we just did sine of 89. That's really, the answer is really 0.99.
The correct answer is 0.9998. Blah, 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 blah.
So don't leave it as just 1.
This is our approximation. That's what we are asked. It says, use a, yes, Ricky, any questions?
I think I'm good.
Okay, use differentials to estimate. We're not asked to punch it in the graphing calculator and get a number. I just wanted to show how close it is. But you're not, you should check. Of course you should check, just to make sure you're on the right track. Any questions? Okay, let's read the last problem here. A particle is moving along the hyperbola xy equals 8. As it reaches the point 4 comma 2. So now remember, this is the word when. And something in the related rates, when you get to the word when, or something that implies the word when, remember these have to wait until the end, right? So these are numbers that cannot be taken into account from the very beginning. So anytime you encounter when or as it, ... or whatever, something like that, remember 4 comma 2 has to wait till the end of the problem. The y-coordinate is decreasing at a rate of 3 centimeters per second. How fast is the x-coordinate of the point changing at that instant? So this may not be a huge difference, because I also have something else in here, which is rate of change. But please remember, do not start with that. Okay, so I'm given xy equals 8, and I'm asked to find how fast is the x-coordinate of the point changing at that instant. What am I asked to find?
dx over dt.
Awesome. Excellent. Indeed, this is what I'm asked to find. Given blah, blah, blah. Given what? Given this, what is this piece? What does this piece mean?
Oh, dy over dt.
But also remember, the key word here is, so what is the rate then when I write dy over dt is? Yes, negative 3 centimeters per second when x is 4 and y is 2. All these have to wait till I'm done with dx over dt. I cannot make use of them. They all come after the word when or the implication of when. So disregard all this. I need to find that. Bless you. How do I find this? I differentiate. You can solve for x if you want, but I would rather differentiate implicitly. But yes, you can solve for x. Let's solve for x. Harvey had the question. Is that what you said, Harvey? Okay, that's fine. Harvey says, let's solve for x, which is perfect. Brilliant. But then I will change this into 8 times y to negative 1. Regardless of whether you solve for x or not, you will still have to use implicit differentiation. Both x and y are functions of a variable, which is time. So be very careful. That's why I prefer myself to use implicit differentiation on this, but why not? Let's see what we get with this. The same thing, of course. Okay, so then we differentiate the left and we differentiate the right. What do we get on the left-hand side?
dx over dt.
Indeed. What do we get on the right-hand side? Negative 8 times y to negative 2 times.
dy.
Right. This is the reason why I think that this is easier. I'm not saying it's wrong. I'm saying it's perfect. But this will be easier to differentiate. But in this case, you will have to use the product rule. It's up to you. Here, use the product rule. Here, use the power rule. One or the other. So then dx over dt equals -8 over y squared and dy over dt. Now I'm done. So I have dy over dt at -3. I have x equals 4 and y equals 2. And I just put in all the numbers. -8 over 4 and times -3. So whatever this is 6. 6 what? This is centimeters per second. Very good. Okay, now let's check. This says how fast is the point, how fast the x coordinate is changing at this instant. So that's the answer. And it's increasing. It's a positive quantity. Any questions? Yes, go ahead.
When we differentiated, I'm just confused on where the -8 over y squared is coming from.
I have to differentiate a function raised to a power. I have to bring the power in front, subtract 1 from the power, and differentiate the inner side, the inner function.
So then what's the next step after that? Because you're trying to find dx over dt.
I already have the x over dt on the left. I just brought this down because it has a negative power. It goes to the denominator. Is that okay? Other questions for me? Other questions? Say it again.
What's the unit? Is it meters per second?
Centimeters.
Centimeters.
Sorry about that. Centimeters per second. Any questions? This was with implicit differentiation, but let's do the other. Let's do the other one. Very good. xy equals 8. We differentiate both sides. Product rule. First function prime, dx over dt times y plus x times dy over dt equals 0. Is this okay?
Yes.
And we are after this. So then dx over dt is negative x divided by y dy over dt. So I had to move this term to the other side and divide by y. I moved the term, it became negative x dy over dt, and I divide by y, I get negative x over. And now I have dy over dt equals -3, x equals 4, y equals 2. So negative, the top is 4, the denominator is 2, and this is -3. And we get the same thing, which is 6 centimeters per second. Yes, please, Frederick.
How do we know dy over dt is -3?
It was given in the problem. That's why I copied it several times. This was given in the problem from the very beginning, but I didn't. I made the point that this is not to be used till the very last step. Good. Other questions? Other questions for me here? I want to say one more thing about the test, and then I will suggest how to proceed today. I cannot stress enough when I will sit down either tonight or tomorrow to write this test, or this weekend since we have the test on Tuesday. I cannot stress enough I will look at the problems we did in class. So please review the problems we did in class, of course, and homework. Okay? Any questions? Is there any particular type of problem? I always ask that of my students. Is there a particular type of problem that you would like to go back to? Something that you would like to see again? Something that it doesn't have to be today. You can also ask questions on Thursday, yes. But is there anything that pops up or comes to your mind right now? Anything that you would like to go back to? Anything? Okay. So you can still bring your questions on Thursday, right? And ask questions. Okay. We still have about 15 minutes, so let's proceed. Let's start chapter 4. Of course, what we cover today and what we will cover on Thursday is not covered by our test 2, of course. The entire chapter deals with applications of differentiation. Applications of differentiation. And the first application that we will look at is max-min. When a function has a maximum or a minimum. That's our first application, which is 4.1. Okay. So let's take a look at a graph. This is a graph of a function f of x. We discussed this before, but I need to refresh our memory on it. Would you agree that this is what it's called a local max value? Why is it a local max? It's because I can show the open interval left and right. Okay, now let's draw some of the tangent lines before the maximum. So here's the tangent line before the maximum. Here's a tangent line before the maximum. Here's another tangent line. Let's draw the tangent line at the maximum. What is the slope of this line?
0.
Correct. What type of slope will these have? Indeed, positive slope for all those tangents. Now let's graph a few on the other side. Tangent here, tangent here, tangent here. Some of them may be underneath. Doesn't matter. So what is the slope of this? These? Yes. Then if this is a minimum, the slope of the tangent line will be 0, but it will be negative and then positive after the minimum. Would you agree? So can I say that on this piece, the function is increasing? Can I say that between these 2 points, the function is decreasing? And can I say that now the function appears to be increasing? So we already established something very important, that the function is increasing when the derivative is indeed. Excellent. And the function is decreasing when the derivative is negative. We're jumping ahead a little bit, however. Let's choose a function and analyze it. Of course, we have other things in between, but I like to choose a function. On page 281, I'm going to pick 30. 281. F of x equals x squared plus x cubed, sorry, plus 6x squared minus 15x. X cubed plus 6x squared minus 15x. What type of function is this?
Quadratic.
Degree is 3, yes, so it's a polynomial. A function that has, and I'm going to write it as a note, a function that has a max or a min, it must have something called critical number. If a function does not have a critical number, it cannot have a max or a min. So note, a function, any function, must have at least one. I'll say critical numbers or critical number. I'll put in parentheses critical numbers in order to have a max or a min. If it doesn't have a max or a min, if it doesn't have a critical number, it will not have a max or a min. So, question for you. All critical numbers, allow me to abbreviate, all critical numbers result in max min? The answer is no. So I will say, okay, we look at a function, we find critical numbers. Is there a guarantee that those critical numbers mean max min? No. So there is an extra step in there. Okay. Our next note. A critical number or critical numbers may come from two possible situations. There's nothing else. So if a function has critical numbers, I have to check if it has critical numbers coming from, first situation, f prime of x being 0. And the second situation, from f prime of x being undefined at x values or value where f of x is defined. Okay, this is a lot. Let's go back from the beginning. So a function, in order to have a max or a min, it has to have critical numbers, or at least one critical number. Perfect. Will those critical numbers change into max min? No. There is an extra step in which I have to test. Okay, now how do I determine critical numbers? I have to look at two different situations. First situation is I have to find the first derivative and set it equal to 0. Solve the equation. Solve the equation. The second situation is I have to look at f prime and see if at any point in time, at any x value, f prime is undefined at an x value at which the function is defined. Because if f of x is not defined at 5, and f prime of x is not defined at 5, that is not going to be a critical number. So, but if the function is defined at 5, but f prime is not defined at 5, then 5 becomes a critical number. If f prime is undefined at 5 and f is defined at 5, that could be a max min. It's definitely a critical number. So let's apply this concept for this function. Either way, I have to find f prime. So let's find f prime for our 30 on page 281. So f prime, can anyone give us f prime?
3x squared
So 3x squared, very good, plus
12x minus 15.
minus 15, thank you. Minus 15, perfect. So now the question is, this function can have critical numbers. I don't know if it does or not. But critical numbers can come from two sources. Not really. Can this be ever undefined?
No.
No, it's a polynomial function. So with this particular function to have critical numbers, the only chance is f prime of x being 0. If I don't get any x values, let's say this is never 0, what will I say about the original function? Does it have critical numbers? If I don't find any here, I will say no critical numbers. Does it have max min? Of course not. If it doesn't have critical numbers, it will not have max min. So let's set this equal to 0. 3x squared plus 12x minus 15 equals 0. Of course, always try to make things simple. It doesn't always work. So this is x squared plus 4x and minus 5 equals 0. And this is x plus 5 and x minus 1. And we have two options. And here they are. So this particular function has two critical numbers, x equals -5 and x equals 1. Will this give max min? I don't know. Here's what I need to do next in order to identify that. And then after this, I'll stop. So -infinity to infinity, -5 and +1. Here is f prime of x. And here's f of x. Obviously 0 and 0. Okay, so all I did was I looked at this function. I found its critical, its x-intercepts basically for the derivative, but we're not graphing the derivative. So I found that the function, the original function, has two critical numbers, one at -5 and one at 1. And now I would like to study the sign of this function. Once again, why am I studying the sign of the function? Because if it happens to be positive and 0 and then negative, what type of point will this be? Max. If it happens to have the sequence negative and then 0 and then positive, what type of point will that be? Minimum. So for this function, let's plug in -10. 3 times 100, 300 minus 120 and minus 15. What is the sign? Very good. Now it's easy because I have 0 in between. Let's plug in 0. 0, 0, negative. And on the other side, if I plug in 10, I'll have positive. Let's also determine this y value. So the function at -5 and at function at 1. So I plug in the graphing calculator. I have x cubed. And then plus 6x squared. And then minus 15x. Okay. And I wanted -5 and I wanted 1. So 100 and -8. At -5 is 100 and at -8 at 1 is -8. Okay, coming back. So I know the end behavior. We know the end behavior of this function. It's a cubic function, and the leading coefficient is positive. So on this side will be -infinity. On the positive infinity will be positive infinity. So I know this already. We can find the limits. So now from -infinity to 100, what does the function do? Increase. Is that supported by the sign of the first derivative? Yes. From 100 to -8, what does the function do? Is that supported by the sign of the first derivative? From -8 to infinity, what does the function do? Is that supported by the sign? So what do we conclude about this point? What will you say about -5, 100?
Increasing positive.
Local max. What will you say about the point 1, -8? Definitely a local min. So this is what this chapter is all about, meaning